Ramps, pulleys, and forces. In this lesson, we're talking about tension, pulleys, solving Atwood machine problems, the ramp, and lastly, solving ramp problems with friction. Tension. The tension force, or T, is the force that is transmitted through a string, rope, cable, or wire when it's pulled tight by forces acting on opposite ends. The tension force is directed along the length of the wire and pulls equally on the objects on the opposite ends of the wire. So the tension force is located where that line is, it's also located there, there, and it's pulling in equal directions all the time. So tension is not going to have a direction, it's going to be directionless. Tension is the same throughout the rope. It doesn't matter whether you're pulling against someone or against the wall, tension is constant. So think about two scenarios. One is that you have two people pulling on a rope, and the other scenario is that you have one person pulling on a rope that's attached to a wall. In both these scenarios, the rope doesn't move. In the first scenario on the top, the person on the right is pulling with a force of 100 newtons, and since the rope isn't moving, the person on the left must also be pulling with a force of 100 newtons to the left. In scenario 2, the person on the right is again pulling with a force of 100 newtons, but that means the wall must also be exerting a force of 100 newtons to the left. So it doesn't matter if it's person-person or person-wall, the tension in the rope is going to be the same. The tension in this case, it depends on which perspective you're looking at, so that's why we don't have a direction. But either way, the tension in the rope is going to be 100 newtons. Tension in pulleys. A pulley is a wheel with two raised edges, you can see that here, right there, and there, right there, so that a rope or string will run along the wheel without coming off. It's a simple machine that can be used to do work, so you can use a pulley system to lift a mass that would otherwise be too heavy. Tension in pulleys. Tension is the same throughout the entire rope in a pulley system, like we just talked about previous. So what would be the tension in the string here? Well, since we have a mass of 2 kilograms, you're going to have your Fg value equaling mg, which will equal to 2 times 9.8, which equals 19.6 newtons. So since there's a force down of 19.6 newtons, there must be a force up of 19.6 newtons, and there must also be a force left of 19.6 newtons. So the tension throughout the string must be 19.6 newtons, and it's directionless because it depends on where you're looking at it from. Pulleys. The masses are held stationary, then released. What do you think is going to happen? Well, assuming it's a frictionless pulley with a single string, our mass 2 is bigger than our mass 1, and therefore the whole thing is going to turn this way. This mass is going to pull it down that way, and this mass 1 is going to go up that way. So we're going to get a clockwise motion. Now, when we say Atwood machines, this is what we mean. It's going to be a pulley with two masses dangling on either side. So how do we solve these Atwood machine problems? Well, number one, we're going to draw a free body diagram of each mass with T being the force up and Fg being the force down. Decide which way the masses will move. The greatest mass will produce the greatest Fg and move downwards. Choose a positive direction for each, while making the positive the direction of motion. And this can be different. So I'm going to show you what I mean. So in this case, since the motion is clockwise, we know the left mass is going to go up, and we know the right mass is going to go down. We know the tension values are the same. So these vectors here need to be drawn exactly the same, whereas our Fg values are different. This mg is twice this, so we draw it about twice as long. Since we say the left mass is going to go up, we're going to say that up is positive for the left mass, and since we say the right mass is going to go down, we're going to say down is positive for the right mass. We can differentiate this because we're going to separate our equations out as we go forward. So what do we do now? Well, we're going to find F net for each. F net is going to be tension minus Fg, or Fg minus tension. It's going to be the larger value minus the smaller value. In this case, it's going to be Fg minus tension because our Fg is bigger. In this case, it's going to be tension minus Fg because in our left mass, we know it's going to go up because the tension is bigger than the force of gravity down. We're going to say F net equal to ma for each. We're going to isolate T in the first equation, substitute the value of T into the second equation and solve for A, and then we're going to substitute A into equation 1 and solve for T. Check your understanding. Find the magnitude of acceleration and tension of an Atwood machine in which m1 is equal to 0.2 kilograms and m2 is equal to 0.4 kilograms. So number 1, find F net for each, and number 2, set F net equal to ma for each. Okay, so we're going to find F net for each. We know that this guy is going to go up and m2 is going to go down. So for m1, we're going to call that equation 1, and m2 we're going to call equation 2. So for equation 1, we know that F net is going to equal to tension minus Fg, and for equation 2, we know that the sum of the forces, or F net, is going to equal to Fg minus tension. Now we're going to set each equal to ma. So for equation 1, it's going to be sum of the forces, which is going to equal to tension minus Fg, is going to equal to ma. And for equation 2, we're going to say the sum of the forces is going to equal to Fg minus tension, which is going to equal to ma. Now we can plug our numbers in. Tension minus Fg, remember that's mg. M is going to be 0.2 times 9.8 equals 0.2 times A, and that gives us tension minus 1.96 equals 0.2A. And then for equation 2, we're going to have Fg, which is again is mg, so 0.4 times 9.8 minus T is equal to 0.4A. 0.4 times 9.8 is 3.92 minus T equals 0.4A. So we're going to isolate T in the first equation. So there's our first equation right there. To isolate T, we're going to bring 1.96 to the other side of the equation. Now we're going to have T is going to equal to 0.2A plus 1.96. We're going to substitute the value of T into the second equation and solve for A. So the second equation is right here. So we get 3.92 minus our T value equals 0.4A, and our T value we just figured out was 0.2A plus 1.96. Remember, the T values are the same, so we can substitute the T value from equation 1 into 2, and then we're going to solve for A. So we're going to simplify. We're going to say 3.92 minus 0.2A minus 1.96, because that negative multiplies there and there. It's very important to do this step, otherwise you can make silly mistakes, equals 0.4A. We're then going to group like terms and solve for A. So we get 3.92 minus 1.96 equals 0.4A plus 0.2A, and we get A equals to 3.27 meters per second squared. And we're going to say clockwise, because we know it's going to go like this, and that is clockwise. We're going to substitute A into equation 1 and solve for T. So equation 1 is T equals to 0.2a plus 1.96. We're going to take our a value, and this a value actually was 3.266. So we can use that number right there. So 3.2667, and that gives us a T value of 2.6 newtons. Now we need 2 sig digs in our answer, so our final answer for T is 2.6, and for A, it should be 3.3 meters per second squared clockwise. Check your understanding. Blocks A and B are connected by a string passing over an essentially frictionless pulley as shown. When the blocks are in motion, block A experiences a force of kinetic friction of magnitude 5.7 newtons. If MA, so that's this guy right there, equals 2.7 kilograms, and mass B equals 3.7 kilograms, that's this guy here, calculate the magnitude of the acceleration of the blocks and the tension in the string. So hint, solve the same way we just did, but keep in mind what F net will mean for A. So like to pause the video and answer this question. So the first thing we're going to do is we're going to draw our free body diagrams. So for A, we know it's going to have a tension force this way, but it also has a friction force this way. For B, we simply have an FG down and a tension up. We're going to say that down is positive for B, and we're going to say that right is positive for A. Now we're going to do the exact same thing. For equation 1, we're going to say the sum of the forces is going to equal to, in this case, it's not tension minus Fg, it's going to be tension minus friction equals Ma. Tension minus friction, we're told, is 5.7. Mass is 2.7, and A we don't know. For equation 2, we know that the sum of the forces is going to equal to Fg minus tension, which is going to equal to Ma. Fg we know is Mg, and that's going to be 3.7 times 9.8 minus T is equal to 3.7a, and I need to redraw this here. We know that Fg is bigger because it's going to move in that direction, so I'm going to redraw my T to look like that, and that's more proper. Now we're just going to expand this out. For B, 3.7 times 9.8 is equal to 36.26 minus T is equal to 3.7a. Now we're going to isolate T in number 1. We're going to say that T equals 2.7a plus 5.7, and we're going to substitute T into equation 2. So we're going to have 36.26 minus our T value equals 3.7a. Our T value is 2.7a plus 5.7. We're going to expand it out. 36.26 minus 2.7a minus 5.7 equals 3.7a, and we're going to solve for a. We're going to solve for a by simply collecting like terms and finding the a value. So 36.26 minus 5.7, and then we're going to divide that by the a values, which is going to be 3.7 plus 2.7. Our a comes out to 4.775. Now we need 2 sig digs in our answer, so our final answer is going to be 4.8 meters per second squared clockwise. Now to find b, we're going to substitute our a value into equation number 1. We're going to say that t is going to equal to 2.7 times a, which is 4.775 plus 5.7. And that's going to give us a t value of 18.6. We need 2 sig digs, so we get 19 newtons. And that's our final answer. Check your understanding. A, does the system move? If so, which direction? B, if so, what is the acceleration? And C, what is the tension in the string? So we're going to do this the exact same way we've been doing the other ones. We're going to set up our 2 equations. So for equation 1, it's going to be the sum of the forces is going to equal to tension, this is being pulled that way by tension, minus the force of kinetic friction equals Ma. The only difference in this question is we need to figure out what friction is. So friction is going to be equal to mu times Fn. Mu we're told is 0.5. Fn is going to equal to mg, which is going to equal to 10 times 9.8. And that gives us a friction value of 49 newtons. So we're going to have tension minus 49 equals 10a. Equation 2, sum of the forces is going to equal to Fg minus tension. That's going to equal to Ma. Fg is going to equal to mg. M is 20 times 9.8 minus tension is going to equal to 20 times a. Then we're going to simplify. 20 times 9.8 is equal to 196 minus t equals 20a. In equation 1, we're going to isolate t. We're going to say t is going to equal to 10a plus 49. And we're going to substitute that in to equation 2. So we're going to have 196 minus 20a. Our t value is 10a plus 49. And then we're going to simplify. We're going to say 196 minus 10a minus 49 equals 20a. We're going to collect like terms, and we're going to solve for a. And in this case, a is going to equal to 4.9 meters per second squared clockwise. Last thing we need to do is solve for t. We're going to substitute a back into equation 1, and we're going to say that t is going to equal to 10 times a plus 49. A we figured out was 4.9, and that gives us a t value of 98 newtons. So we have an a value of 4.9 and a t value of 98. Now in this question, we're given the information, but we're not given a picture, so we need to draw the picture out as we go through the question. What I'd like you to do is pause the video and answer this question in exactly the same way we've been answering the other ones. But this time, make sure you draw the diagram before you start. So let's draw our desk. We have our pulley, we're going to have our string, and we're going to have our 2 masses. We know the mass of the hanging block is 0.1 kilograms, and we know the mass of the stationary block is 0.196 kilograms. We're also told that mu is equal to 0.4. So we need to find the acceleration and the tension, just as we've been doing. Just like the previous question, we need to find the friction as well. Because when we draw our free body diagrams, we know that we're going to have an Fk going to the left and a tension going to the right for our green, our mass number 1, And for our hanging mass, we're going to have an FG value going down and a tension value going up. We're going to say that down is positive for red and right is positive for green. So for our first equation, we're going to say that the sum of the forces is going to equal to tension minus Fk equals Ma, and we need to figure out Fk. So let's do that over here. Fk is equal to mu times Fn. We're told that mu is 0.4. Fn is equal to mass times gravity, so 0.196 times 9.8, and that gives us an Fk value of 0.768 newtons. So we can plug that in. So our sum of forces is going to equal to tension minus 0.768 equals 0.196 times A, and then we're going to isolate T. T is going to equal to 0.196 A plus 0.768. For equation 2, we're going to say the sum of the forces is going to equal to Fg minus tension, and that's going to equal to Ma. Fg is going to equal to mass times gravity, so 0.1 times 9.8 minus T is equal to 0.1A, and then we're going to simplify and we're going to say 0.98 minus T is equal to 0.1A. We're going to substitute 1 into 2, right, this into the T value, so we're going to get 0.98 minus tension equals 0.1A, and our tension value is 0.196A plus 0.768. We're going to simplify, we get 0.98 minus 0.196A minus 0.768 equals 0.1A. We're going to collect like terms, and our A value is going to become 0.716, and to two significant digits, that equals to 0.72 meters per second squared clockwise. We're going to substitute that into equation 1, and we're going to find T. T is going to equal to 0.196 times A plus 0.768. Our A value is 0.716, and that gives us a T value of 0.91 newtons. And those are our final answers to two significant digits. Technically, this question should have one significant digit because we have 0.4 and we have 100. So our final T value should equal to 0.9 newtons, and our final A value should equal to 0.7 meters per second squared clockwise. Now, ramp problems aren't too different from what we've been discussing so far, but there's a few more forces acting that we need to keep in mind. Remember that Fg is going to be equal to our mg, which is down. So in our diagram, our Fg is right here. Keeping in mind our object, however, is on a ramp. Fn is perpendicular to the surface. If the surface is here, our Fn is going to act perpendicular to that surface, and Fn is not going to equal Fg. Friction acts against motion, so if our tension is going to the right and up the ramp, then our friction is acting down the ramp, and the angle of the ramp is going to be equal to theta. Theta, the angle of inclination, is going to be very important to our calculations. So if our ramp is at an angle of theta 1, then when we draw out our diagram, you're going to see what that looks like after. That's going to be our object. Our Fn is going to be perpendicular to the surface. Our theta 2 right here is going to equal to our theta 1, and we're going to need that theta value to figure out our forces at work. Now you can see the forces that we're talking about. The force that's opposite to Fn and equal to it, so Fn is going to equal to Fg cos theta, and that's going to be equal to this one right here. Fg is going to be this Fg, but it's going to be a component of it. Just like this component right here, Fg, is going to be a portion of the total Fg, and that's going to equal to Fg sine theta. That's going to be the force acting down the ramp. So if you have an object, you're going to have a force acting down the ramp that's equal to Fg sine theta. You're going to have a force acting up the ramp that's equal to Fk. You're going to have your Fn that's perpendicular to the surface, and you're going to have your Fg, which is at an angle. So how do we solve our ramp problems with friction? Well, they're very similar to Atwood problems. We're going to create our free body diagram for each separately. We're going to write out our Fnet is equal to Ma equation for each object. Don't forget that Fnet is the sum of all the forces acting, so don't forget friction. Make one equation 1 and the other equation 2. For equation 1, we're going to isolate T and simplify. We're going to substitute the answer for T from equation 1 into equation 2. We're going to solve for acceleration, and then we're going to substitute acceleration back into equation 1 and solve for T. Check your understanding. A block on an inclined plane of mass 5 kilograms is attached via a massless rope over a frictionless pulley to a 6 kilogram weight hanging over the side of the incline, and you can see that right here. The mu k value is 0.5 and theta is 30 degrees. What forces are acting against the motion? There are two. Once you've found that out, I want you to find the magnitude of the acceleration of the system. So if we were to redraw, we have our ramp and we have our object on our ramp. Our object is attached to another object via a pulley system. This mass is 5 kilograms and this one is 6 kilograms. The mu value is 0.5 and theta is equal to 30 degrees. So the first question asks what forces are acting against the motion? Well, we always have friction, and when we're dealing with ramps, we're also going to have this component right here, our Fg sine theta. You can see that force is acting down the ramp, and therefore it's acting against the motion, which is up the ramp. So it's Fk and it's Fg sine theta. Find the magnitude of the acceleration for the system. So first of all, we need to draw our free body diagrams. So for our block on our incline, our free body diagram is going to look like this. We're going to have T, we're going to have Fk, we're going to have Fg, and then we're going to be able to break that Fg into two components. We're We're going to call this FG cos theta and FG sine theta. And then we're going to have Fn that way. For the other block, it's pretty basic. It's simply just going to be Fg down and T going up. So for equation 1, we're going to say the sum of the forces is going to equal to tension going up the ramp. And we're going to say that right and up are positive and down are positive for that one. So going back to equation 1, sum of the forces is equal to tension minus Fk minus Fg sine theta. And that's going to equal to Ma. T is going to equal to Fk. Fk, we can figure out over here. Fk is equal to mu times Fn. Mu, we're told, is 0.5. Fn, remember, is going to equal to this Fg cos theta. So Fg cos theta, 0.5 times Fg, which is equal to mg. We know that mass is 5 times 9.8 times cos 30 degrees. And that gives us a force of friction of 21.2 newtons. So tension minus 21.2 minus Fg sine theta. Fg again is mass, which is going to be 5. G is 9.8 sine 30. That's going to equal to the mass, which is 5 times acceleration. Now we're going to simplify. So we're going to have T minus 21.2 minus 24.5, that's this together, equals 5a. So we're going to get T equals 5a plus 45.7. So that's getting T on its own, so skipping one step and bringing these two together and on the other side of the equation. So that's going to be our equation 1. So that's going to be equation 2 right there. That's 6 kilograms. So we're going to say the sum of the forces for equation 2 is going to be equal to Fg minus T, which is equal to Ma. Fg is going to be mass times gravity. So 6 times 9.8 minus T is going to equal to 6a. 6 times 9.8 is going to equal to 58.8 minus T equals 6a. And then we're going to substitute our T value into that equation. So we're going to say that 58.8 minus T equals 6a. T is equal to 5a plus 45.7. We're going to expand it out. 58.8 minus 5a minus 45.7 is equal to 6a. We're going to collect and we're going to simplify. We're going to get an a value equal to 1.19 meters per second squared clockwise. We're going to use 2 sig digs in our answer, even though technically that has 1. We're going to use 2 in our answer. We're going to say a is equal to 1.2 meters per second squared clockwise. And that's what we have right here. B says find the tension on the rope. Equation 1 was tension is going to equal to 5a plus 45.7. Our a value, remember, was actually 1.19, and we're going to substitute the numbers in. T is equal to 5 times a plus 45.7. A is 1.19, and that's going to give us a T value of 51.7 newtons. And then we need 2 sig digs, so our final T value is equal to 52 newtons. Check your understanding. 2 masses, 4 and 6 kilograms, are connected by a massless rope over a frictionless pulley as pictured in the diagram. The ramp is inclined 30 degrees, and the coefficient of kinetic friction on the ramp is 0.18. A. Draw a free body diagram of both masses. And B. Determine the magnitude of the acceleration for the system once it begins to slide. So I'd like you to pause the video and answer these 2 questions. Okay, so for A, we're going to be looking at our 2 masses. So our first mass is going to have tension, friction. It's going to have Fg, and then it's going to have its components of Fg. That's going to be Fg cos theta, and this one's going to be Fg sine theta, and then we're going to have an Fn like that. And that's going to have a mass of 4 kilograms. And then for our second mass, we're going to have Fg, and we're going to have tension. Now determine the magnitude of the acceleration of the system once it begins to slide. So we're going to call this equation 1, and we're going to say that right and up are positive. And we're going to call this one equation 2, and we're going to say that down is positive. So for equation 1, we're going to say the sum of the forces is going to equal to tension minus Fk minus Fg sine theta equals Ma. We need to figure out Fk. So let's do that right here. Fk is going to equal to mu times Fn. Mu, we're told, is 0.18. Fn, we know, is going to equal to Fg cos theta. So Fg is going to equal to mg. So the mass is going to be 4 times 9.8 times cos 30. And that gives us a friction value of 6.11. So we can put some numbers in. T is going to equal to 6.11 minus Fg. Again, that's mg. So it's going to be 4 times 9.8 times sine 30. It's going to equal to 4a. And then we can simplify and say that T is going to equal to 4a plus, I'm going to add these 2 together, 25.7. And that's going to be our equation number 1. Equation number 2 is going to be the sum of the forces. That's going to equal to Fg minus T equals Ma. Fg is going to equal to mg. The mass of this object is 6, so we're going to say 6 times 9.8 minus T is going to equal to 6a. 6 times 9.8 is equal to 58.8 minus T is equal to 6a. Now we're going to substitute T into equation 2. We're going to have 58.8 minus T equals 6a. T is 4a plus 25.7. We're going to simplify 58.8 minus 4a minus 25.7 equals 6a. And once we collect like terms and solve for a, we get an a value of 3.31. We need 2 sig digs, so we get 3.3 meters per second squared clockwise. C says determine the tension on the rope. So I'd like you to pause the video and figure out T. So remember, our A was actually 3.31, and there's equation number 1 that we're going to need after. So determine the tension on the rope. We're going to have T is going to equal to 4 times A, which we said was 3.31 when we're using the unrounded version, plus 25.7. And that gives us a T value of 38.94 newtons. We need 2 sig digs in our answer, so we're going to say T is going to equal to 39 newtons. D. If the rope breaks when the 4 kilogram mass is 3 meters from the bottom of the ramp, how long will it take for the mass to slide all the way down? Include a new free body diagram and assume the sliding mass starts from rest. So what does this mean? There's our ramp, 30 degrees. The rope holding the block snaps. So now you're just left with the block, and it's going to start sliding down the ramp. Now, since our motion is going to be to the left, we're now going to have friction acting up this way, and everything else is going to be the same. That's our Fg. That's going to be our Fg cos theta, and that's going to be our Fg sine theta. This is still going to be our Fn. The 3 meters is this right here. So what I'd like you to do is pause the video and find out how long it's going to take for the mass to slide those 3 meters. So T is going to be our question. You know, the distance it's going to slide is 3 meters. You know, the VI is 0 because it says start from rest, but we do not know the acceleration, and we do not know the VF. The variable that's going to be useful in this question is acceleration. So we need to figure that out, and then we can figure out T. So how are we going to figure out the acceleration? The sum of the forces acting on the object as it starts to slide down are going to be the force going down the ramp, which is this Fg sine theta, and that's going to be counteracted by the Fk going up the ramp because the Fk is opposing motion. And we're going to say that's going to equal to Ma. Fg is going to equal to mg. We know the mass of the block is 4 kilograms times 9.8 times sine 30 minus Fk. Fk is going to be the same number we found in the previous example. Just because the mass is now sliding down the ramp doesn't mean that the Fk changes. Fk is still going to equal to mu times Fg cos theta. And we found that number out to be 6.11. So Fk is still going to equal to 6.11. So minus 6.11 equals 4a. Now we can simplify and we can solve for a. 4 times 9.8 times sine 30 is equal to 19.6 minus 6.11 equals 4a. A is going to equal to 19.6 minus 6.11 divided by 4, which is equal to 3.37 meters per second squared down the ramp. So we can put that number in here, 3.37. So now what equation can we use? We can say that D is going to equal to VIT plus 1/2 AT squared. We know that VIT is going to equal to 0 because VI is 0. D is 3 equals 1 over 2, 3.37 times T squared. We can isolate T squared. It's going to equal to 3 times 2 divided by 3.37, and that's going to equal to 1.78. And then we can find T by taking the square root of 1.78, and we get 1.33 seconds. We need 2 sig digs in our answer, so we get a T value of 1.3 seconds, and that's the time it takes to slide down the ramp. And that concludes our lesson on ramps, pulleys, and forces.